I'm going to be working a problem involving constant acceleration due to gravity. The problem states that a football is kicked with an initial velocity of 12 meters per second in the horizontal direction and 22 meters per second in the vertical direction. How long did the football stay in the air, find the maximum horizontal and vertical displacements? So after the football leaves the kicker's shoe, it's going to travel in a parabolic arc. And we have a two-dimensional position graph here. So the trajectory of the football is going to look something like this. And we're not given a whole lot of information in this problem. We're given basically the initial velocity. So let's write that really quickly. It's given to us here verbally. It says initial velocity, so we're going to call this v. It's a v vector, and it has two components. So it has a 12 meters per second horizontal component. So that's 12 meters per second in the positive x hat direction. And then it says we have a 22 meter per second component in the vertical direction. So this is 22 meters per second in the y hat direction. So that's the vector equation that describes the initial velocity. It's going to be the slope of this line immediately after the ball is kicked. Why do I say immediately after? Well, because immediately after the ball leaves the kicker's foot, you're going to then have acceleration that's working on the ball due to gravity, and it's going to be pulling it downwards at every point along the ball's trajectory. So this little gravity vector is pointing downwards, but this is working at every point along this ball's trajectory, and it's going to eventually make it reach a point here at the maximum height of the arc, where the velocity in the vertical direction is equal to 0. What's the other thing that we learned? The other thing we learned is that the horizontal velocity doesn't change throughout the trajectory of the football. So it would remain the same over all periods of time, and it would continue this way because there's no acceleration that's acting in the horizontal direction. So Vix is constant, and it equals V final in the x direction. It's going to remain the same in the beginning all the way to the end. So the V initial in the x direction equals V final in the x direction. It's just going to continue. So one thing that we have to notice, and you kind of have to just think about this, and it's not immediately apparent, so, if this isn't something you realized, well, that's perfectly fine. There's people who have thought about these problems for a very long time. And one thing that we can note is that the initial velocity in the y direction, the magnitude of that is going to be equal to the magnitude of the velocity in the y direction at the end of the ball's path. And what do I mean by that? So if I have this green vector here pointing upwards 3 blocks, it's going to point downwards 3 blocks over here at the very end of the ball's trajectory. So this would be, we can call this V initial in the y direction, and this over here we can call V final in the y direction. And V initial in the y direction, the magnitude of it equals the magnitude of V final in the y direction. So the signs are going to be different. I mean, this one's pointing upwards and this one's pointing downwards. So clearly one of these, this one, is negative. But the magnitude is the same. The length of these vectors is going to be the same. And how can we explain that? It's kind of difficult to understand just looking at this graph and trying to figure that out. But if you remember the x and y components of the velocity, the horizontal and the vertical components are completely independent. So we can think of the vertical velocity on its own. So we have the vertical velocity. Well, we know that its maximum velocity is right after it's kicked upwards. And then gravity is going to start slowing it down For each instance of time, it's going to get slower and slower and slower until eventually it's going to stop. And here, Vy equals 0 at the top of this path. And then what happens? Well, again, gravity's pointing downwards, so now it's going to start moving downwards. And you might just be able to figure it out by thinking about it a little bit, or maybe you have an intuition, but this vector here is going to be exactly equal in magnitude to this vector right here, because the acceleration's constant. So if I started out at, say, 20 meters per second, and then I got to 10 meters per second over 1 second, and then I got to 0, well, then I'm going to be back on this side, 0, a negative 10 meters per second, and then negative 20 meters per second. This is pretending that gravity is equal to 10 meters per second squared. So every second, it's changing by an additional 10. So your speed at the very end is equal to the speed that you started with in the vertical direction. It's just a different sign. And that's what I'm trying to indicate over here with these green vectors. So one is pointing upwards, it's positive. The other one's going to be equal in magnitude, and it's pointing downwards. Now, this is assuming we have some horizontal area that we're standing on. But if you had, for example, some lower area down here that the ball could travel to, well, now this trajectory is going to continue, and your V final is now going to be larger than your V initial in the Y direction. Why? Well, because it had more time due to having more space to accelerate from gravity. But that's not what we're dealing with right now. This problem, you could figure out what this new height that was traveled, you could use the new height to figure out what your new speed would be here at the bottom, but that's not what we're doing. We're working with like a football field that's perfectly level, it's perfectly flat, and the height when we kick it is the same as the height when it lands. So those are just some things to keep in mind. But now let's solve this problem now that we have all these things that we've discussed. What is it that we know now? So we can say, well, if V initial in the Y direction equals the magnitude of V final in the Y direction, I see that it's equal to 22 meters per second. And I know that the final in the Y direction has to be negative, so my V final in the Y direction is equal to negative 22 meters per second. And what is my value for acceleration due to gravity? This is something we're going to use over and over again. Eventually you'll have it memorized because we use it so much, but it's 9.81 meters per second squared. So we don't have a few things. We need to find time. How long? Well, this is indicating time. So we don't know the time. We're going to figure that out. So I can write here t, we're not sure. And we're also looking to find the maximum horizontal and vertical displacements. So we'll call this delta x and delta y. And we'll call these both max for the maximum. Okay, so where do we go from there? Obviously, we're going to have to use one of our kinematic equations, most likely. And what can we use? Well, we have to look again at everything that we have as far as the quantities that are given to us. So let's just look at this last part first. So how would we find horizontal and vertical displacement? Well, my equations for horizontal displacement, we know that there's no acceleration. So it would be delta x is equal to some velocity in the x direction times a time. Remember, we wouldn't have a 1/2 at squared because what's the acceleration in the horizontal direction? Well, it's 0. There's no acceleration in the horizontal direction, so that term is 0. And we're only worried about the first term of the equation, the Vx times t. Okay, well, I don't have time. I do know what my velocity in the x direction is, and actually let's write that down. It's right here in the first part of this vector equation. My velocity in the x direction is equal to 12 meters per second. So I have my velocity. I'm trying to find this displacement, but I don't have a time. So I'm going to have to use an equation that helps me find time. Well, what do we have? So we know that one of our vector equations says the velocity final in the y direction is equal to the velocity initial in the y direction plus what? Well, it's going to be an acceleration times time. Acceleration times time gets me a velocity. And what is the special acceleration that we use in the vertical direction? Well, that's g. So this acceleration is g. Now let's look if I have these values. Okay, I have a VIY. We discussed that that's the maximum velocity vertical direction when you start, and we discussed that the magnitude's equal to the final velocity in the y direction. We also know what g is, that's constant. So we can use this equation to solve for time. So I'm going to do that. Now my goal is to isolate or solve for time. We need to figure out what the time is, because the amount of time that the football is in the air that we discover from this vertical kinematic equation is the same amount of time that the football spends in the air while it's traveling horizontally. These times are the same. Whether it's from this equation or this equation, these t's are equal. So I'm going to solve for t. So I'm taking this equation, v final y equals v initial y plus gt. What would I do first to solve for t? Well, I would subtract this VIY from both sides, minus VIY. And I have now v final y minus v initial y. That's another way of writing delta v. This is the change in velocity, the final minus the initial. And this is equal to gt. And now I just divide by g. So this becomes t equals v final y minus v initial y over g. And that's great. Now I can input my numeric values, and this then becomes t is equal to, well, now I have to be careful. I have a negative sign here. So it's going to be v final y is negative 22 meters per second minus VIY, which is minus 22 meters per second. All of this over what? I'm going to have a negative number up here, and I'm looking for a time. Which direction is g pointing? Well, g points downwards, so that means that g is going to be a negative 9.81 meters per second squared. So this is equal to a negative and a negative, so this is a minus 44 meters per second divided by a minus 9.81 meters per seconds times seconds. I'm writing it that way just because I want to see that I have two factors of s, And then I can see more clearly that I have a meters per second in the numerator, and I have a meters per second in the denominator. And I'm left with 1 over seconds. And we've practiced our complex fractions now. We know that 1 over 1 over seconds is just seconds. So this seconds is going to come up top. I'll say that one more time. 1 divided by 1 over seconds is seconds. The two negative signs become positive, and this is then 44 divided by 9.81 seconds. And I'll put that in my calculator here. It's going to give us a decimal value. So 44 divided by 9.81. And that to 2 decimal places, then t becomes 4.49 seconds. This is one of the quantities that we had to find. It asked us how long this ball would be in the air. This time is the same whether you're considering the vertical equations or the horizontal equations. So we've found one thing that we needed. Well, now I can go back and look at my horizontal equation now. So now I can look at my horizontal equation. I can say, okay, what do I have here? Well, I know my velocity in the x direction. That stays the same the entire time since the horizontal component of velocity is not affected by gravity. And now I know t for time. So I can solve for the horizontal displacement, that is delta x, the change in position in the x direction. So I'll do that. So now I have delta x equal to v sub x t. And this is equal to, well, v sub x is 12 meters per second. And t is 4.49 rounded seconds. So now I'm going to use my non-rounded value and I'm going to multiply that by 12 to get delta x is equal to 53.82 to 2 decimal places. This is seconds divided by seconds, and this should be meters. That makes sense because we're talking about a change in position. So that is the correct unit. So that is the one component of our answer that we needed, which was the horizontal displacement. We're left now with one last thing to solve for, and that is the maximum vertical displacement. Now, when we look at the graph, we can see that our maximum vertical displacement is not going to be over here. This is the maximum horizontal displacement because that's how far it traveled horizontally. But since its position is changing and it's changing signs, it's going increasing and then decreasing in the vertical direction, because in this direction the velocity is causing the position to increase vertically. It's getting higher and then it's getting lower. So over here the position is decreasing. So if it was getting higher and over here it's getting lower, well, then if you just look at the graph, you should probably be able to figure out that, oh, well, this is the maximum height. This is going to be the maximum vertical displacement. And how do we find what that value is? Well, it's going to be halfway through the trajectory of this ball. So if we use a kinematic equation for position, for example, it's going to be now delta y. We've learned so far it's delta y equals Well, you have now some v initial in the y direction times t plus a 1/2 at squared. And what is a in this case? Well, the acceleration is gravity. So it becomes g. Notice I specified here that this is the initial velocity times t. And over here, when I talked about delta x, I didn't specify an initial or a final. Why? Well, because we stated here and we figured out that the initial and the final are the same, so I didn't have to specify that when I'm dealing with the horizontal direction. In the vertical direction, I need this to be my initial velocity in y, which is going to be a positive number. This number here is going to be positive. It's pointing upwards. It's at its maximum at the beginning. So what would we do to account for the fact that we're not traveling the entire length of this trajectory when we're finding our max height? This is y max. Well, we simply divide the time in two. This is symmetric, this shape, this parabola, it's symmetric. And we can see that we're only traveling half the time to get to the maximum height, and then the other half the time we're traveling downwards. We're accelerating downwards, the velocity is going downwards, and the position is decreasing. So, okay, well, I'll just write a new t here. So now I'll have t sub 1/2. Just giving it a name. So if I write t here and I give it a new value, well then which t am I talking about? T has to only have one value in this problem. So I have to give it a new name. And t of 1/2 is 1/2 times t, which is 4.49 seconds. So I can put that in my calculator. So 0.5 times the value for t, and t of 1/2 becomes rounded to 2 decimal places is 2.24 seconds. So that is just this portion up here, and I apologize, it's getting a little cramped, but it's this portion right here. So this is the value of t I'm going to use. And I'll go ahead and write and specify this over here. I'm going to use t of 1/2, a little subscript, just so we know what we're talking about. So now I can plug everything into my equation. I believe I have everything else. I know the initial y velocity. We figured out t of 1/2. We know what g is. This is the same t. So we can go ahead and solve this. So I'm going to go ahead and input my values here. VIY is 22 meters per second. T of 1/2 we've just found is 2.24 seconds plus 1/2. And here I need to be careful. So which direction is G pointing? It's pointing downwards, so this needs to be negative 9.81. That's meters per second squared. And then I have t of 1/2 squared. So t of 1/2 is 2.24 seconds, and that whole thing needs to be squared. The seconds needs to be squared as well as the numeric value. You might be wondering why we don't specify g to be positive or negative from the get-go. And just as a quick aside, sometimes we'll have a problem that's only working in one direction. For example, if I would drop a little baseball from some height, we can actually treat downwards as positive. We decide which directions and what means positive or negatives when we define our coordinate system. This isn't something that has to always be positive x. you could define right as negative x. So sometimes if you're working only in one direction and you don't have two different directions that you're having to keep track of, you can just keep everything positive. So in this case, I could say, well, we're going to treat gravity as being positive and the downward direction as being positive. So that's why I don't specify it. If it confuses you, you can always just write negative 9.81 meters per second squared. That's entirely up to you. It is something that you always have to think about. Okay, which direction is gravity pointing if you don't always specify it as negative? So now I just need to simplify these numeric values. So for example, okay, let's take the 22 times 2.24. This first term becomes 49.34, rounding to 2 decimal places. And the seconds divided by seconds is 1. That leaves me with just meters. Now I'm going to pull out this negative sign, and I'm just going to put it in front of these numbers. So this becomes minus, and I'll do the 1/2 times 9.81 to start. So 0.5 times 9.81 gets me 4.91 rounded, and this is meters per second squared. And then I'm going to square the last term, so it's 2.24 squared. This gets me 5.03, and I have to also square the seconds. So now I'm going to combine these last two terms. This 4.91 times 5.03, so we see a seconds on the denominator, a seconds in the numerator. So this then becomes, we have 49.34 meters minus 24.67 meters. And then the last step, we just do this subtraction, and the final value is 24.67 meters. And this is delta y max. If you got a little bit of a different value, it's probably because I was using the non-rounded values when I would do my intermediate steps. But this is the final answer for delta y max, and that indicates the maximum height that the ball would achieve at the top of its trajectory. So that is, again, this point over here. It's the maximum displacement in the vertical direction that the ball achieves. The total horizontal displacement is this 53.82 meters, and the time that the ball spent in the air is t equals 4.49 seconds. So that was a lot. That was a big problem. I'm going to be working some more problems just so we get comfortable with this. And the probably most difficult part is determining where to start. Once you've written down all your values that you're given, determining what equation is it that we have to use. You have to basically check and see, okay, do we have everything except for one unknown? Can we solve for just the one unknown with everything else that we've been given? So that's just something that you have to learn through practice, but we'll be doing more of these problems in the future.